Hello, welcome back. This is my third video as part of the OpenFOAM tutorial on shotSleeveModeling, and in part 2 of this video series I've gotten as far as constructing the mesh for a geometry just like this, just like the one you see in this figure, and now I'm going to show you how we can actually make this geometry moving. And for this purpose we can go back to our terminal and address the most important file for this mesh motion first, which is the dynamic mesh dict. It is located in the constant folder of your case. So gedit constant dynamic mesh dict, opens it. And we can see here that as the dynamic mesh of class solid body motion FV mesh has been selected. We don't want that, of course, because we don't have a solid body that is in motion. We want to have something else, something that moves ourselves. So we can just put bananas, for example, for using the infamous banana trick. Go back to our terminal, sending the gedit in the back, and execute move dynamic mesh, which basically tells OpenFOAM to do the solving without the solving. So it only solves for mesh motion, but not for the field properties in the CFD domain. If we do this, we'll see that bananas, of course, as we intended, is no valid FV mesh class, and that we have to choose one of these. And the one that we want in this case is dynamic motion solver FV mesh. So we just highlight it, Control Shift copy, C actually copies something from the terminal, paste it into your dynamic mesh dict file, save that, and do the move dynamic mesh one more time. It will then immediately tell us that the keyword solver is undefined in the dynamic mesh dict. So of course we are good boys or girls, and define therefore the keyword solver. Since none of us has an idea what to put, just put blah, for example, save it once more, and ask OpenFOAM to tell us which solvers are available. Unfortunately, in this case it's not that easy, because it simply replies solver table is empty, and the reason for this, to find out, is not entirely straightforward, but lucky for you I'm going to show you right now how to fix that issue. And the problem is that we didn't include the particular motion solver lib, which is done with this motion solver libs command. But once more, we don't have any idea what we could actually put there, so I'm going to show you how you could equip yourself with at least some ideas on what to put there. And you can do this by using the ls command on Linux, and in this case we want a ls foam libbin, and this will list all the available libraries. Fortunately the list is pretty long, so if we want to get a rough idea on what we actually could use for our problem, we could filter that list, or in other words grab through that list with this with the same Linux command. So I'll do the ls foam libbin one more time, and this time I'll pipe the result to the grep command. Now grep for motion, for example, and this gives me the result libfv motion solvers, which is just the one we want. Control Shift C copies it, so we can simply paste it to our dynamic mesh dict file. Save it. Move dynamic mesh one more time, and ta-da! It will now tell us which solver types are available. And for this tutorial I picked the layered motion. And in order to give us some ideas what this displacement layered motion solver actually needs, I'm gonna look at the source code first, and since I got no idea where the source code is, I'm going to use the grep command one more time. gonna grab for this place layered motion, and I'm gonna grab in the directories recursively, of course. This tells me that there are quite a few files that have this displacement layered motion in the name, and the one I want is the .h file, because the .h file is the header, and this normally gives additional info on how the solver works, or at least in this case it does. And if I highlight this line that leads to that includes the path to the h file, scroll down, gedit, press the mouse wheel, which will paste the path to the terminal, enter. So, and I now have opened the source code, the h file of the source code. Scroll down to description, I can see there that the mesh motion solver, this mesh motion solver for multi-block extrude FE mesh, gets given the structure of the mesh blocks and boundary conditions from these blocks, and the displacement layered motion course subdict in the dynamics mesh dict must be defined, and it defines the region, which is a cell zone. I'm going to get into that later. And for this cell zone it defines the boundary conditions on two opposing patches, which means one patch at the one end and one patch at the other end, and it interpolates the mesh motion between these two patches based on what kind of boundary conditions you specify for these patches, and these patches have to be phase zones. It interpolates, as I said, using topological walking, and it therefore requires a layered mesh, which is not a problem since our block mesh dict has nearly perfect layers. The available boundary conditions for the phase zones are currently follow, which follows the overall mesh displacement, and it uses the proper boundary conditions set in the point displacement, which is another file that the solver needs, but I'm going to get into that later, and uniform follow, and fixed value, and time varying, fixed value, and slip. But for this tutorial I'm only going to use fixed value and follow. Okay, I'll leave that open for one more minute, but I can already tell you that we won't need this subdictionary for the solid body motion FE mesh coefs, so we can get rid of that. But instead we need to write another subdictionary, which is called displacement layered motion coefs, and for the sake of the efficiency of this tutorial video, I'm not going to tell you step by step by doing the banana trick over and over again how I actually got there, but I'm going to show you now just simply which entries to put where. And as it also said in the H file, it needs the subdictionary regions, and inside the regions it needs a cell zone, and this cell zone I'm going to name moving cells. There is right now in the mesh not yet a cell zone that is called moving cells, but I'm going to create that later, and I'm going to show you how to create it, so please be patient for one more minute or maybe two, and I'm going to show you how to create it, and trust me that I will get into it. We also need to define the entry interpolation scheme, and I picked linear in this case, and of course we need to specify the boundary field, which was also mentioned in the .h file. And the boundary field we need to name the two phase zones, moving phases. They are also not yet present in the mesh, but I'm also going to create them later. And the moving phases are of course of type follow. They are supposed to follow the boundary conditions. And the other phase zone is boundary. And if you followed me through part 2 of this tutorial, you also already probably recognize which set of faces I'm going to assign to this face later on, because the naming is quite similar to the naming I used when I created the block mesh dict. Okay, these are of course of type fixed value, and the value in this case is 0 because I want them to be fixed. Okay, that's that. And all for us left to be done is close each of the subdictionaries. Okay, done. We can save this file for now and go back to our terminal and try to execute move dynamic mesh one more time. It will tell us quite immediately that we cannot find the file point displacement. Okay, so what are we going to do now? Probably be best to create a file that's called point displacement, and we do this by grabbing through the tutorial files and find one. That we can just easily modify. So there we got quite a couple of these, and we can just simply pick one. For example, this one, which comes with InterDimFoam. First, I have to create a 0 folder again, because I immediately deleted it when I was deleting all the other results. And then we can copy the point displacement into that file, into that folder, our 0 folder. We can look at it in gedit. Okay, this of course is for another case, and so we delete everything we don't want. And of course we don't have any patch that is called inlet, but we have a patch that is called moving walls, for example, and a patch that is called outlet, so this can stay. And for the outlet, for example, we can also keep the fixed value, but another patch that we also want to have the fixed value for are the fixed walls. So we can combine these two, since we want to have the same boundary conditions applied for this, by using this regular expression. OpenFOAM fortunately can read regular expressions, so whenever it looks for the outlet boundary conditions or the fixed walls boundary condition, it will just go into this subdictionary, which is quite convenient because we don't have to repeat it, and in particular if we want to make adjustments for adjusting boundary conditions or anything like that, we don't have to do it 2 times in here. Okay, so what else? What other pictures do we got? We of course got slip walls, which are the walls where it is sliding along, and the slip walls are of type calculated. The value entry we don't need in here. Okay, slip walls, and as you remember, the only patch that is left is moving walls and front and back. Front and back, and front and back, of course, is of type empty. Empty. Good. So the only thing that is left to be done is moving walls. Moving walls is a bit tricky actually, because it has to be of type solid body motion displacement. and solid body motion function is linear motion. And then the solver gets a bit weird actually, because it wants the subdictionary linear motion course, which is the subdictionary. And it needs the entries there once more. Solid body motion function, linear motion. And another linear motion course. And then in another subdictionary the velocity. And now if we remember how we defined our block mesh, you will be able to remind yourself that the layers of the moving part of the shot sleeve actually grew into the negative z direction, so we want the velocity of the mesh motion to be executed in positive z direction. Therefore, and as I want to have the motion to be 1 meter per second, I put 001 here, which means 1 meter per second, as also the unit indicates that we want to have 1 meter per second in z direction. Okay, so that's it. Just put for ParaView 1 meter here, and it also needs the velocity for whatever reason once more outside the linear motion course in here. Okay, so this is about it as far as the point displacement file is concerned. We got the slip walls type empty. We got the no, I did a mistake. Of course, I made all the entries for outlet, but fortunately I can easily adjust that. Simply renaming that. Fixed walls outlet type fixed value. Okay, check. Moving walls type solid body motion displacement with all the complicated entries as I specified. Okay, this so far does look alright, so we can save it. And the only thing then is now left to be done is how to do the topo set of the mesh. And this will be part of the next couple of minutes in this tutorial. And I'm going to show you how to use the toposet dict for that. And since we don't have any toposet dict, which is normally located in the system file, see, no toposet dict in here. We need to find one, and we do this by using the grep command once more. And grep through foam, no tutorials. Okay, so should be quite a couple of them, because normally toposet use something you need for quite a lot of solvers. Let's just take this one, for example, multi-phase interdim foam DCT hull, and I can take it by just highlighting it once more. Okay, copy it. This is looking wrong. So maybe just pick another one. Looks better. Open it in gedit once more. There it is. And what we're going to do now is modify these actions according to our needs. And we have to create 2 face zones and 1 cell zone. And in order to, let's start with the cell zone, maybe because this is normally easier. And we need to name this cell zones moving cells. And we do this by creating a cell set first. So the action is a new cell set. Box to cell also is good. And we can go from -1 meter to 1 meter in x direction, because that doesn't really matter, because we want the entire domain. We can also go from -1 meter to 1 meter in y direction. And now it gets a bit tricky. We want to go from want to go from -1, but not all the way till the end, but only till -20 e minus 3, because all the rest should not belong to our moving cells face zone. Okay, now that we have created the cell set, we have to transform the cell set into a cell zone, and we do this by using the newly created cell set. This time we don't want a cell set, but a cell zone. Cell zone set actually is the proper term, and action new is okay. And then we want to have the source. The source in this case is set to cell zone. Set to cell zone, and source info we have set moving cells. Okay, so far looking good. And now we have created the part about the cell zone. Next will be the face zone, and we have the proper entry already. And we can use, for example, moving. Let's start with the moving faces first. Face set is okay. Action new, patch to face. I'm not going to use this one. Should be okay, but it at some point caused me problems, which I decided to go for the box to face here. Box to face, and the source info will be a box, of course. So just copy this, and once again going from -1 to 1, because it doesn't really matter, and I'm going to go from -30 e minus 3 to 30 e minus 3. Okay, and for the moving faces, if you remember, they are precisely at -300. I'm going to go from -301 e minus 3 to 299 e minus 3, minus 299, of course. Okay, so now we have a face set, and what we need to do is make a face zone out of this face set, and we can use the entry here for this purpose. Put it underneath, a bit of readability, and we call this moving faces. Face zone set, new, set to face, works, face set, not F0, but moving faces. Okay, so this is face zone number 1. Second face zone, this we don't need, can delete it. We'll just create analogously. Copy these entries. And we don't need them, name them moving faces, but as we said, boundary moving fixed, boundary moving fixed, face set first, and then a face zone set. And we also have to adjust the box, because we want to now just simply go from -29, E -3 to 19, -19, E -3, which should capture exactly the amount of faces that are right at the boundary between the moving and the fixed area. Okay, so far the only thing we need to change is here. Boundary moving fixed. Okay. Let's try that we don't have any typos. That's looking good. It's looking good too. Okay, let's go to shot. Give it a shot by going back to the terminal and type topo set. Okay, so here something's gone wrong apparently. Cannot find, oh, probably something I should have, or did I just simply not save it? That could be the problem. Yes, indeed. Try this one more time. That looks good. So I got now 15 faces in the face set moving faces. I got 15 faces in the face set boundary moving fixed, and I also got 15 faces in the cell zone, and I got 502 faces in the cell zone moving cells. Just to make 100% sure that I actually grabbed the right ones, I can use partIII for that. Let's wait and hope and see. Okay, there it is. Once more, I need to make sure that we do not load any fields. Okay, but I don't want to load the internal mesh this time. I don't want to include the zones, and I want to show moving cells, cell zone. Click apply. And for whatever reason it selected the internal mesh again. So if I deselect the internal mesh, this part should disappear. And look at that, it does. So that worked. And I see the moving faces. They are here, they're supposed to be, but for whatever reason I can't see the boundary, or is it just because, yeah, there it is. Check this too. I see, just as I wanted them, two opposing face zones that are inside one cell zone where it's supposed to calculate the mesh motion on. Okay, with having set up the files just as mentioned, there's one more thing to be done, which is in this case adjust the control dict. I can do this by opening it, and I want to set the end times to 0.25 because I want to have it compressed and not having the mesh move beyond its actual target. And write interval can stay, I think, and I just increase the time step because the mesh motion is normally known not to be super time sensitive, and I can also delete all these functions from the control deck because we don't need them here in this case. And yeah, okay, so that looks alright for now. Let's see if I'm right with this estimation. I can just try to do the move dynamic mesh. See how it's working. It's looking okay, at least it solved all the way to the end. Okay, good. Just deselect, make sure the point fields are deselected once more. Click apply. I want to see the internal mesh. Pick one of these, and if you click here on adjust camera and say roll -90, you will also have the proper orientation. Let's go for surface with edges, and you can see now it does exactly the mesh motion as we intended it to do. So we can put a check behind that and proceed to the next part, which will be the adjustment of the boundary conditions. So I conclude part 3 of the tutorial now. Thank you once more for your attention, and see you back at part 4.